Hi, welcome to engineering. Today I'm going to be explaining an example for the two curve. Now, two curves is basically if we go into our example or our circumstance, our scenario, we'll see that we have roads that has two curves on it, which we have to do the calculations for the chainages, parameters like the radius and tangent lengths, as well as the staking values. So if we look at our question, we'll see that A, B, C, D are consecutive intersections on the road. And the first thing that means is we have all these values which are points on the road. They're either PI values or the beginning and end of our road. Then they are connected by straight sections. So this means that there is a straight road between each of the curves. And the first curve starts at D. Now this is very important because you would just assume A, B, C, D is the sequence. But since we start at D, we need to know the sequence will start at D and continue along the road. Once we plot the points on the sketch, I'll show you how we would consider this. Then we are given sets of coordinates for these different values, including coordinates for E, which I'll explain now briefly. So we first have to calculate the radius of curve 2, round off until the nearest meter, and change distances for all points relative to the road. I'll also show you that in the sketch. Then we have to calculate staking values for the second curve. So we will be ignoring the first curve when it comes to staking, only do the second curve if the instrument is set up at the end of the curve and staking values of 100 meters is used. Now some important points to know is E is the start of the second curve. The radius of the first curve is 850 meters, and the change distance at B is 67,852.457. So this is all the given information to us. So I think the first step that we would need to do is actually draw our sketch. So first thing we do is we plot out all the coordinates. And you'll see that they sort of work in a sequence of a Z shape. Now, or it's actually an S, sorry. Now, the reason why we can connect them is because we said they are consecutive points on, or intersections on the road. So that's our first hint. So D, C, B, and A are all connected. Now, why I said it in that sequence is because we start at D, which means from D to C, C to B, and B to A, we have consecutive points on our road. Now the next thing we need to notice is that E seems to lie on the line between C and B. If we go back to our coordinate, that's how we plotted it, but we must also see that E is the start of the second curve. So what does that mean for us? It means that we have a road that sort of goes from D to A, and E is start of our second road. So if we're traveling along the road in this direction, and this is the beginning of our curve, we can safely assume that the end of curve will be somewhere around here, and that this is our second curve. Now our first curve must therefore be somewhere in this area. We can't have a curve outside this obtuse side. That's too large of an angle for the curve. Also wouldn't make sense. So because we know this is going to be part of the straight road and this is going to be part of the straight road, we can know that our curve is inside here. Alright, so the first thing we need to do is calculate our joins and test them with polars. If you don't know how to do this, I have a separate video that explains how to calculate joins and polars. So what we'll do is we'll calculate a join from D to C. Then this will give us our distance and direction between the two. The next step will be from C to B, B to A, and then from E to B. Now the reason why we do it from E to B is very important, and note that I highlighted the distance that we calculated in blue. So all those joins give us the distances and directions between our points. Alright, so now the first thing that we need to do is determine where our curves were. As I explained now, this is roughly what our curves will look like. So this means that from D to BC1, around this curve, EC1 to BC2, or where E is the beginning of curve, along this curve to A. That is our road. Now our road flows. In other words, these two lines over here and these two lines over here are our tangent lines. They are the tangent to a curve that both meet up at a value which is our pi. Now what we need to calculate is the theta for our curves. Now the theta, we have to consider these two lines. We say from the start value to the pi value, we have to say this direction, if we extended it, minus the direction from our pi to end value will give us this angle over here. Imagine this line extended here, this line over here is our theta, and that will be theta 1 for curve 1. So therefore we say the direction of D to C minus the direction of C to B, and that will give us this angle over here. Now the reason why we add 360 is because DC is smaller than CB, so it'll give us a negative answer. We cannot have a negative direction or angle, so we add 360 to it, which makes sense. Then from C to B and B to A, we have another curve. We extend C to B, which is our start, to pi value, then we extend it this direction, then we can have start to pi minus pi to end, which will give us this angle. Once again, it will be a negative value, so you plus 360. Alright, so that's how we get our theta values or our deflection angles. Now the next set of calculations have strict formulas, so please stick to these formulas. The first thing we'll be able to do, which is very easy for us, is we calculate tangent length 2. Now this is an exception to me saying that we have strict rules, because if we go back we will see that we have E and we have B, so it's very easy to calculate this distance. Now we can use that value with the formula to calculate the tangent length to calculate our radius for this curve. So we basically reorganize our formula, say the tangent length equals to R2 times tan of deflection angle divided by 2. We have the deflection angle as well, which gives us our radius for the second curve. So everything with 2 represents second curve, everything with 1 represents the first curve. Now the radius for the first curve was given to us, so 850 meters, so that is fine. Then from there we need to calculate our tangent length 1. We do have the radius, we do have the deflection angles which we calculated, so we can put those into the formula and get our tangent length over here. Now notice that these tangent lengths are actually theoretically smaller than the first tangent or second tangent lengths that we calculated, even though the sketch does not represent it like that. So I need to highlight that this is not to scale, it's just for demonstration purposes. Alright, now the length of curve has a formula of theta times the radius times pi divided by 180, because we have it for radians. So the length of curve, we have our deflection, we have our radius, and pi is a constant, so we can get our length of curve for 1. Now the length of curve is this length over here. It is from the beginning of curve to the end of curve. Then for our length of curve 2, we can do the same, put it into the same formula, and we get the length for this. Once again, the sketch is not very accurate, so you'll see that some of the measurements do not make complete sense. But if you do this properly, plotted it on a graph paper, you would see it will make sense. Alright, so now we have our BC1, EC1, BC2, and EC2. So beginning of curve, end of curve, beginning and end of curve. We can now calculate our chainages. Now, chainage B is given to us, so we can work with everything from there. Some advice I would like to give you is try to work with points on the road as far as possible. The only exception is if a PI is given at the chainage. But because B and C are PIs, they are not actually actual values on your road, So you must please remember that they're not actually on the road, so this having a chainage is just an extension from this straight line here. Okay, so with that being said, we calculate our BC2, this value over here, by saying this chainage minus this length. And the reason why I say minus is because we have to consider that we are traveling along the road from D to basically to curves and to A. So the direction of what I indicated now. So to go from B backwards on the road is minus. And that's why you'll see lots of minuses. So we have change of B minus this tangent length, and will give us our beginning of curve chainage. From there we can calculate our EC2. Now the EC2 for both curves are very easy. All it is it's this chainage plus this curve of the road to get the next chainage. So I mean, it makes sense. To get from one point and you travel a certain distance on the road will give you the other chainage or that distance from the road. So that's a very easy calculation. Then to get our chainage A, which is not always necessarily the end of the road, but in our scenario it is, we would just say this chainage plus this length. Now the way we calculate this length is we can take the full length of AB minus this little section, which is the tangent length, and we can get this distance from EC2 to A. So this will be this chainage plus that length of AB minus tangent length 1, or tangent length 2, sorry, and that will give us our chainage for A. Now something I need to highlight is your two tangents on each curve are the same. So this length and this length should be the same. Alright, now for EC1, it's a little bit more complicated. We need to work out what's this length between BC2 and EC1. Because we're going backwards, we know we need to minus a distance. But now to get this distance, the best way we can do it is we can consider this tangent length, and the full length which we calculated of CB. So what we'll do is we'll say CB minus this tangent length and minus this tangent length to get this distance in the middle. So that distance in the middle, you say BC2 minus that length will give us our EC1. Alright. Then for BC2, the opposite to what we did over here is we say EC2 minus the length of curve 1, and gives us our BC1's chainage. Then for D, all we have to say is take the full length of CD minus the tangent length to get this length over here. We'll say BC1 minus that length gives us chainage D. And then for chainage C is the last one. Now chainage C is not actually a PI, or it's not actually a point on the road, but just for its sake we calculate chainage C by saying D plus the length we calculated with the join to get off DC gives us our C chainage. But change of C and change of B are not points in the road, so you should not always consider them. For example, if you take chainage C and you try and add the length to EC1, it's not going to give you the same answer as what we calculated, because BC1 is to consider the curve, where EC1 takes these two tangent lengths into consideration. Alright, so that's quite a long explanation, but hopefully that makes sense to you now. Alright, then for the staking. Now this is an important part. The first thing we need to do is we need to calculate the first subchord and the last subchord, because our normal subchord is 100. Now a subchord is basically all, okay, so we're working with chainage 2, curve 2. So we want to basically stand on a point, in this case at the end of curve, and look at at certain angles, so we can plot out where our curve should be. Now remember that we are traveling on the road basically just in a southern direction down this way, where we will be working with EC backwards to BC. So don't let that confuse you when we do the staking now. But because we're traveling from this direction, sometimes our chainages for our beginning of curves, end of curves, or almost always actually won't land on a perfect chainage of 100 meters. It will land a little bit before one and a little bit after another one. So, or that same one actually. So if we have a chainage and then we have our BC, we'll still have an interval of 100 somewhere just after our BC's value, which in this case will be 67,100. So we say that little point somewhere here minus our BC's chainage will give us that subchord. And the reason why we call it a subchord is because it's not a full chord of 100 meters, it is a part of it. So this value and this value will always be less than the chainage. For the last chainage, we know that we have an interval and then we have EC, which is somewhere in the middle of the last one on the curve and the next one that's not on the curve. So what we have to do is we have to say EC minus that little one to get that little extra piece at the end, which is 94.276 meters. You see both of them are under 100 meters. Alright, so why these are important is we can calculate our angles. Alpha 1 is subchord, with the first subchord's value times 90 divided by pi radius. While alpha 3 is the last subchord's value, this value over here, the 94, times 90 divided by pi times radius, which will give us this value over here. And then the alpha 2 is our normal sub, so we just put 100 meters in there and it will give us that angle. Alright, so these angles are consecutively going to be added from one to the other or subtracted from one to the other depending on the scenario, so that we can determine basically the different directions we need to measure from a point. So in this specific example, we are going to work backwards, and the reason why we work backwards is because we are standing at EC2 and we are working our points backwards to BC2. So first things first, it's anti-clockwise, which means it's negative, so our direction is decreasing as we go along, and that's why we go, and as well as we are working backwards on our road, so our chainage decreases as well as our direction is going to decrease. Now please take special note, we are on the end curve. So what we want to do is we want to take the direction from EC to B, which is 209.53, and we want to say minus values to get eventually to this point. So because we're at EC, we first have to consider our last subchord, because we have to go from the last one into the curve. So we're going to say direction minus our last subchord and gets us a new direction, which is direction to the first internal chainage. From there, we're going to work with the constant 100 meters between, so 100 meters, 100 meters. We're going to go backwards in 100 meters, so we're going to say direction minus that equals that. That direction minus the same constant chainage equals a new direction. Direction minus alpha gives a new one. Direction minus alpha, and so on, right until we get to the last one, the 67,100, before we get to our, actually that's supposed to be beginning of curve. Sorry for that. That is beginning of curve. So now that we're at the beginning of our curve, that last little piece before we get to beginning of curve should be our first subchord. So then we say this direction minus our first subchord gives us a new value, or gives us a new direction. Now there's three ways to check this. Okay, so the first way we'll do is we will, okay, as I said with the arrows, we go down, we get to this last value, then we say the bigger direction minus the smaller one will give us a certain amount of angle between the two, which in this case is 23, 14, 13. Alright, now why we want to calculate this is because we want to compare it to another two values. Now a very important value is if we take our theta, which we calculated originally, and divide it by 2, we'll get 23, 14, 13. So please take note that this is probably the easiest one to calculate, and you should know that your answer at the end of this table should equal this value. And since these two match, we can safely say that we've already done all our calculations correctly. But we do have a third check, which is we add all the alpha values together, because obviously these alpha values are the difference between the first one and the last one. Now, an easy way to do this is you count how many ones are in the middle. So this 1 degree, 28 minutes, 27 seconds is, there are 14 of them. So you say that times 14 plus this one plus this one, it gives you the same answer. Then you can confidently say that you've done your calculations correctly, that everything has worked out. Now, something I just want to highlight to you is often we'll, for example, work from the BC to the EC. If we work from BC to EC and we are turning right, so imagine you're coming down this road and you are turning right, then it's clockwise, so we'll have direction from E to B plus angles. We'll start with the subchord, the first subchord, and end with the last one. That's the normal scenario. Because we do it the opposite way, we obviously add the last subchord first and then the the first subchord last in the scenario. Now, if we go along this road, for example, on curve 1, we are actually turning left, not turning right, because we're going this way. So in a case where we're turning left, if we start at BC, then we minus, because we're going in anti-clockwise direction. If we were standing at EC, looking backwards, because it's a turning left scenario, we'll go backwards essentially on the road, but we'll be going clockwise, so we have to add directions. Alright, so there are basically 4 different scenarios: turning left and turning right, as well as standing on BC or standing on EC. If you've done all this correctly, you can do most curve calculations in this sort of method. Thank you very much, and I hope you guys have a good day.